Yeah, as you might have realized, the title changed as the meeting took place. So in light of the talks yesterday, I decided not to talk about an SNR, given there was already an overview of that and constraints from Planck, in particular on inflation. So I decided to change a little bit of that, and in fact use the opportunity here to talk about constraints on the reionization stream of the universe from Planck, but at the same time use this opportunity to bring up issues related to instrument systematics in the data analysis, because so far we've been hearing yesterday a lot about the foregrounds, foreground contamination, and how prohibitive they might be for digging out the signal B modes and therefore constraining parameterization waves, and their importance for fully constraining inflationary scenarios. So let me move on. So first of all, you saw this plot we had yesterday, but I think it's never too much to stress fantastic achievement of the CMB community within 50 years. It's really remarkable. Not only the CMB and satellite missions, but all the remarkable suborbital experiments that took place. These are the standards, as was mentioned yesterday. And the game at the time was go out and increase sensitivity and increase resolution. Just do it. And we did it. We achieved so far, and from COVID to Planck, exactly that. And we reached at some point what's called nowadays a precision era of cosmology. But we need to move forward now. We are now going even seeking for higher sensitivity. And this, of course, not only means developing the technology to achieve such sensitivity, as well as designing some sort of architecture that will minimize the contamination of your maps, both from foregrounds and instrument systematics. And what that is meaning in time is that this experience is becoming really costly and expensive. But I couldn't not help myself to borrow this slide from John yesterday, and just to show how intense activities ongoing at the moment, covering a wide range of large range of angular scales in the search of many signatures of importance to us. At large scale, polarization looking for reionization, intermediate looking for primary radiation waves, and then going higher L looking for lensing B modes. Indeed, we need sensitivity, angular resolution, and minimizing contamination of external factors. So let me now go quickly to Planck and constraints from Planck experiment. I'll start by showing the 7 CMB maps, polarized maps from Planck. On the top you have the ones from the low frequency instrument radiometers, which encompasses 3 bands, 30, 44, and 70 gigahertz. And the 4 bottom ones, polarization of course, from the high frequency instrument 100 kilometers. You have the Q used parameters and polarization intensity on the right hand side. So these are the maps that were delivered in 2015, and most of them, as you might have heard at the time, were high pass filtered because of the presence of systematics at very large angular scales. Here what I'm showing is the maximum, the posterior of the amplitude, the CMB on the top, synchrotron in the middle row, and synchrotron at 30 gigahertz, and dust emission at 353 gigahertz. Okay. And basically we have this Q and U Stokes parameters for each of these maps. Now, an image that's very interesting, particularly for whom is interested in looking at the magnetic field, magnetic fields and constrained magnetic fields, is actually giving jointly the dust temperature and polarization to 353 gigahertz. Here, as you can see, the total intensity is encoded in colors. The polarization is encoded in shady striations, and polarization orientations of 90 degrees from striations, and indicates direction of magnetic field projected on the sky. It's really very nice. And finally, a very nice image, as ever, is the color composite image of the foreground emission. Here you have in blue the synchrotron emission, green the free, yellow CO, and thermal dust in red. And just for fun, you have here superimposed an image of the celestial sky with very well-known objects. And you might want to do correlations by eye and figuring out where some of these are already present in this particular foreground composite map down there. So this is what Planck has been rendering, not only CMB but rendering quite a lot of information on the foreground emission. of our galaxy, and extragalactic emission as well. But let me now turn my attention to the large-scale CMB polarization. And as I said today, I was going to talk, I'm not going to talk about three modes, but about reionization. So, first of all, we do know that reionization happened. At some stage or another, luminous sources started ionizing the intergalactic medium. And fortunately for us in CMB, you can see that. That can be is imprinted in the CMB anisotropies. Just because you have Thomson scattering of CMB photons and electrons in the presence generating linear polarization from the quadrupole anisotropy of the CMB radiation. This is exactly what happens at the recombination, of course, but here is a reionization later in time, and therefore the signature, which emerges as being this bump in the E and the pulse spectrum, is transferred into large angular scales just because the horizon size sometimes now larger angular scales as well. That's very well known. The point I want to make here, though, is it's a rather difficult measurement to make because it's small and it's confined to very low multiples, as you can see here. Therefore, we need indeed, and is required, to have an accurate control in systematics as well as foreground contamination. Okay, and that's the name of the game, and it's been the name of the game in Planck and Planck team. And as we heard just in the previous talk by Sylvia, some of these things do really drive us crazy. So let me just show now the results from the 2015 CMB late analysis. On the top at low L we have the temperature map, it's a commander temperature map that we used, with applying a mask with a 93% sky fraction. On the bottom here we have the 70 GHz polarized maps, clean from foregrounds with 30 GHz, which is a tracer of cyclotron, and 350 GHz, which is a tracer of dust, applying a mask that gives sky fraction 46%. Then these maps are then converted into, compressed into angular power spectrum estimation on the top, just for the temperature, and here for the polarization. Okay, for that maximum likelihood estimators for that. So first of all, of course, from these data, from this angular power spectrum, or if you want directly from the maps, depending on what likelihood you choose to use, then you can compare your data to models. In particular, in this case, you use the pixel-based likelihood to compare to models, and these are the results we got. On the left, first of all, here I'm talking about constraints using just the low temperature polarization likelihood, not the full range of multiples, okay? Just low L multiples up to 30. And we do that by fixing all the parameters, but those of interest like the optical ionization, NSRS, we leave all the others fixed. To best fit model 2015 coming from the temperature, which is a hybrid approach from low temperature and high L temperature. So if you do that, and in this case an example just for AS and tau, you see the constraints coming just from temperature, for polarization. As you can see, of course, as we all know now, that you cannot constrain using just temperature polarization separately. You need really to have joint information from both in order to constrain nicely and get this very nice counterplotting loop. This is translated now here into a marginal distribution of tau, exactly from the same, with the same color coding here. The main point out of this slide is that this analysis gives rise to a value of tau of 0.267 plus or minus 0.222, as you can see, significantly lower than the one obtained previously. Now let's compare now what you obtain when you do the full analysis with high L incorporated. So when you do the analysis of Planck 2015 polarization using low L and the TT high L, this is what you get. So you can see that there's a shift upwards of tau. If you add on the lensing, then you go down, again, 0.07. And if you add on BAO, you go even farther down, 0.67, exactly the things that we get for just low L analysis. Okay? This is all translated here, of course, in terms of the 1D distributions. Okay? So the solid lines are using just TT, and then incorporating lensing and BAO. The dotted lines are incorporating the low polarization and new likelihood, using 70 GHz data. For comparison, of course, I incorporate here double map constraints, early constraints, the first constraints that we got in tau. You see that the 2015 value had a very high value compared to that, it's 0.089. But the exercise that Planck team did was actually to clean double maps from dust using our dust channel, our 353 GHz channel. And what you see is that the tau shifts downwards to 1.75, as you can see, now compatible to the values obtained from Planck. Notice as well that the error bars here are much smaller, but the fractured sky is much larger. So fractured sky here is of 46%, and here is of the order 70%. Now, by now you might have asked yourselves is, why are we using 70 GHz data? Isn't it the case that, isn't that the case that the HFI channels have lower noise? In fact, initially our decision for 70 GHz was because indeed the noise was well characterized in this map, and we were driven to the conclusion that there was a negligible contamination from foregrounds and from unexpected systematics. However, the HFI channels have lower noise, so we did not choose them exactly because of what? Not foregrounds, because of systematics. Okay. And that's why I wanted to bring a bit of reality here, because yesterday you heard a lot about foregrounds, but it is important to tackle foregrounds not only nodes on right, but along and in its interplay with instrument systematics, which can become quite a headache, in fact, in order to get rid of, in particular polarization, particularly large angle scales. So what I'm going to show now is the work that was done after the 2015 data was published, using just the HFI data, and was published now in 2016. This is a pre to future or upcoming 2017 release. Okay? So we did know at the time that the low L large angle scales HFI maps were contaminated by systematics. And there was then developed a new effort in trying to improve, first of all, understanding of large angle scale systematics in both HFI and LFI instruments, to improve the maps and improve the tau measurement. That was one of the aims. Simulation effort, very important, to characterize systematics remaining data. And finally, one of the things that emerged from here is a new map-making procedure. And of course, the corresponding papers. First of all, let me remind you, I have 5 minutes, right? Okay. So let me remind you that we do not have in Planck an instrument of polarization modulation. In fact, the IQE is solved by combining sky measurements from polarization sensitive bolometers and by sky modulation. Secondly, another important point is that the scanning strategy of Planck and the way it's designed is such that you do not have, or you confront much of the sky is poorly sampled polarization angles. So what does that mean is that you have enhancement, temporal polarization leakage in the maps. And therefore, it is really essential that the characterization of the detector to detect relative properties and long time scale stability of measurements have done adequately and properly. And I'm just showing here the state of the art in HFI at the time. These are simulations of most of the instrument systematics you might have. Just to remind, purely instrumental, you have the analog to digital converter, for example, it is in nonlinearity. You have time response residuals, relative gain between detectors, possible time variable gain. Scans simulated, you can have far side or pickup, zodiacal emission, light emission, bandpass mismatch, which of course gives rise to temperature polarization leakage. And what turned out from the simulations, as you can see from this plot here, if you look, the one that's dominant is this purple line, which is actually the ADC nonlinearity. So at the end of the day, for all of these effects, this was the major one that contaminated the large angle scales polarization map to HFI. Just to give you an example of what that means, if you have a perfectly linear analog to digital converter, you'll have a line that's horizontal around zero. What you see is this. It's very complicated. It's very nonlinear everywhere, in particular around 0 AD. Okay? And you can see that, for example, signal dipole or thermal drifts are shown here for 4 kilometers. So this is complicated, and of course it does undermine or contaminate your maps. There was a huge effort to HFI mission to characterize the ADCs. There were major improvements between 2013 and 15, but some residual effects still remains. So let me move on. Just see the effect of ADC nonlinearity here. These are simulations. I don't think I will have much time to go through all of these, so bear with me. You have simulations here. In this case, you have a constant gain per ring, for example, and here you have ADC nonlinearity included. Now apply the new map maker that we developed, and you see that here we have almost no residuals, and here there is other residuals that are coming mostly from dipole distortion, which are not correctly for the new map making procedure. And this is what is the difference between the red lines on the top and on the bottom, which shows actually the efficiency of the new map-making method in tackling this issue of the ADC by basically using a gain variation correction. I'm going to move on. I can't say just to say that the LFI systematics are very different, are mostly due to calibration uncertainty and far-side log pickup and fatigue area, so it's a different nature. So how did you solve the problem? You developed a new map maker by extending the data model to incorporate all the systematics that you want to reconstruct. And just to give very quickly, you have the time variable again here, another term for residual dipole, another term for bandpass mismatch, residual transfer from zodiac templates, and finally this track of step. So this is what you do. You extend your data model, your map making process, and fit file. And just to show the success of that, you have left-hand side 2015 data and 2016. All these colored lines are basically splits of the data, residuals, as you can see, much larger than what we expected from simple noise. And then using this new map-making procedure, these are very much more reduced and below the signal. So this is just to show the success of this. Then, of course, you have your map-making, you generate your map to compute your file spectra, use 100 times 143 to spectra these two channels. As you can see, we have a very small number of multiples to analyze. And then you apply a simulation, a likelihood that in this case is not a pixel-based likelihood, a simulation-based likelihood, and these are the constraints we have. So using the HFI data, cleaned and controlled and supposedly controlled systematics, you will have an estimation of tau that's even lower and is at the order of 0.55 with an uncertainty of 0.9. So this is basically a summary of all the tau results from WMAP up to the recent from Planck. If you look at terms of time, it's even more striking. It goes down with time, tau. And finally, of course, you say, I reduce tau. What does that imply for example, an amplitude tau spectrum, and that's best? You do cause a downward shift in sigma 8 by 1 sigma. Doesn't resolve the issue, is not sufficient for the tensions with the SC clusters. And of course, you have a slight issue of which not downwards, not upwards, about for sigma. Now, I'm just saying, I think I should possibly just stop here. I'm just showing what you can do then. Of course, you can then constrain models of reionization. Here are examples of several different models of reionization on the left-hand side, and constraints, and how they, for a value of tau 0.06, how they translate into the angle spectrum, CMB spectrum. As you can see, you cannot distinguish them. Tau is low in this particular case. But you can, of course, for each of these models, then try to constrain the redshift reionization and then leave this reionization. And in particular, you can see that constraint comes nicely if we put this prior. We put it prior that the end of reionization happens and the redshift margin sits. So I think this is all for now. Thank you for your attention.